Okay, so now I just want to take some time and go over these magnetic flux practice questions and just kind of clarify anything, get rid of some of the weirdness surrounding these questions. So the first one, we say 100 turn wire coil has a resistance of 400 ohms and a cross-sectional area of 0.010 meters squared. The coil is placed in a magnetic field directed parallel to the axis of the coil. If the field changes at a rate of negative 0.4 teslas per second, what is the current induced in the coil? So we have this idea that our change in flux per time is equal to our EMF, this voltage. So it's just kind of a fancy way of saying, hey, this voltage is coming from you doing something, so we're just going to call it that. But it's pretty much just a voltage, and we know that we have this Ohm's law, V equals I times R. So what we can say is our rate of change of flux over time is equal to I times R. So this thing is nice because it tells us our rate of change of flux. It tells us that it's just 0.4 teslas per second. So our flux per time is just going to be this negative 0.4 teslas per second. And it also tells us our resistance, I, and tells us our resistance is 400. So when we do that out, we get 0.4 divided by 400, and we get 0.001 amps is equal to our current, which is the same as 1 times 10 to the negative third. Okay, so now for number 2, we're saying for number 2, a square loop is located in a region containing a magnetic field of magnitude B. The following figures show 5 possible directions of the magnetic field relative to the loop. For which of the directions is the magnetic flux through the loop the greatest? So the arrow is just showing us the direction of the magnetic field, so I got a little confused when I first did this. It's not showing us the current, it's just literally showing us the magnetic field. So in this first case, there is no magnetic field going through that area because it's all just kind of going on top of it. So the amount of magnetic field passing through is 0, so this one has no flux. With this one, all of the magnetic field is passing through, so we're going to have the maximum amount of flux, so it's going to be B. With this one, it's passing through at this angle, so some of the magnetic field is kind of being lost. We said that we have this like cosine component, so if we think about our area, it's kind of weird because usually we don't think about area being like directional, but area is just going to be this perpendicular vector. We can think about every object as having like this normal vector that is perpendicular to the surface. So in this case, the magnetic field is at some sort of angle away from our area vector, and we said that we want to capture the most magnetic field possible. This will not capture the most. If we think about this flux as being BA cosine theta, over here we have some sort of angle. We know that cosine is maximized at 0 degrees, is just 1, right? So here we have some sort of angle between the magnetic field and the area vector, so that is some sort of angle, which means we're not maximizing flux. Same for this one, and then this is kind of the same argument as A, except for it's just in a different direction. So that's our answer for this one. The amount of magnetic flux through will be maximized if we're capturing the most magnetic field in that area. The figure above shows or I guess figure below, shows a bar magnet and a conducting wire loop that is fixed in place. Which of the following would cause an induced current in the wire? I, moving the magnet toward the loop at a constant speed, rotating the magnet about line X, which lies along the axis of the magnet. 3, rotating the magnet about line Y, which is perpendicular to the axis of the magnet. So what we want to think about first is I'm just going to kind of draw in a magnetic field here. So we know that the magnetic field for just a little pole magnet just looks like this. And we've been saying with this flux that we need to, in order to induce a current, we need to be changing our flux through time. So we need to either change the magnetic field or we need to change the area over time in order to induce a current. If we don't change either the area or the magnetic field through that area, then we will not have a induced current. We won't have a flux, a change in flux that we need. So if we're going through these, if we move the magnet toward the loop at a constant speed, that'll definitely change. If I'm kind of remaking the loop, so that'll definitely change up how much magnetic field is within that loop. If we're close over here, we're capturing more. If we're further away, we're capturing less magnetic field. So if we move it physically closer, that'll definitely do it. So I is good to go. Moving the magnet toward the loop at a constant speed, yeah. Rotating the magnet about the line X, which lies along the axis of the magnet. So if we just spin it like this, it won't change the magnetic field because this magnetic field is really symmetrical around the magnet. So yeah, we kind of just draw it in one plane, but it's happening symmetrically in all of these planes. So that won't change the amount of magnetic field that's going through the loop. Right, we only really draw it as a 2D representation, but really it is this 3D. This is not a good drawing, but that's not really getting my point across. But it's really this 3D dispersion. So it's not just in one plane. In that plane, we have the same amount of magnetic field, so it's just spinning, but it's not changing the amount of magnetic field. So 2 is no good. And then we rotate along line X. Yeah, that'll definitely change it. If we kind of think about the extreme there, if we're at a full like 90-degree out of phase rotation, then our magnetic field is really pointing into the page and out of the page. I guess it would be the same. It'd be pointing, right? Well, I guess I'm just redrawing it. It'll be pointing either into the page or out of the page, and then it won't be going through this loop anymore. So that's kind of an extreme example, but it shows you that 3 is also good to go. So we have 1 and 3 only. This one, a circular loop of wire and a uniform magnetic field rotates at a constant rotational speed about the axis shown. At time t equals 0, the plane of the loop is parallel to the field with point P at the top as shown above left. At time t1, the loop has rotated 180 degrees, so the point P at the bottom as shown above. What? So the point P is at the bottom as shown in this right image, whatever. Which of the following graphs best presents the magnetic flux through the loop as a function of t from 0 to 1? So what we can really think about is at the beginning, we don't have any flux. So we're looking at something that starts off with 0 flux. So this one's no good. This one's no good. This one's in the running. This one's in the running. And this one's in the running. So with this, we start off with no flux because our magnetic field is not going through our area. We also have to end at a spot with no flux. I don't know if, yeah, this one doesn't do it. This one does end with no flux. This one ends with no flux. And that one ends with no flux. So what we can think about is during this one rotation, we have pretty much just a 180-degree rotation. And we have this idea that our flux is equal to B A cosine of theta. So when we're going from 0 to 180, let me pause this really quick and kind of think through how I want to say this.